University of Copenhagen, is Nathalie Wahl, and her title is What the Space Know About the Manifold.
Thank you.
Yeah.
Thank you for the invitation to speak here. It's a pleasure. So I know Dennis from the string topology days, and I'm still in the string topology business. Have had a lot of fun with it over the last many years. So I'll be talking about this question, which I think was probably a reason Dennis was interested in the topic is if you have a manifold, you can associate all the loops, all the strings in the manifold, and then you can ask, well, how much information can you recover from the manifold out of this space of strings? So let me say this a little more precisely. So I'll have a manifold M, and I'll pick a Riemannian structure because it's convenient for me. And then I'll consider this what we call the free loop space, which is the space of all maps from the circles. And maybe, you can decide a little bit what you mean by maps from the point of view of a topologist that I am. I'm thinking of a homotopy type, and there are many models that give the same homotopy, whether you take continuous maps or C-infinity maps, or the ones that are called H1 maps, which are those such that this energy is well defined. Okay, so pick your favorite model. And so in particular, you could look at, if you have a model on which the energy is defined, the energy is a nice enough function, and you can apply Morse theory, and then Morse theory tells you, well, the homology of this space, the homology of the free loop space, is made out of the critical points of that function. Okay?
Rather detail, Morse, the way that Morse theory did this case.
Right. Morse was actually interested in these types of questions. So he was, and in particular this...
Geodesic, closed geodesics.
Right. And so what are these, this way? what are these critical points? These are the closed geodesics. And what is really fun about this fact is that the homology of the free loop space, on the other hand, is an invariant, only cares about the homotopy type of the manifold. So the geodesics are intrinsically a sort of something that depends on the Riemannian structure, but the homology of the free loop space as such does not care about it at all, right? So you have an invariant here that somehow is built out of these closed geodesics, but without having anything to, without in itself caring about the Riemannian structure, okay? I'm going to do something else, which is to have some time on. I forgot. Here we go. Right. Okay, so what's the direct consequence of this fact is, for example, that just a non-zero, the fact that the homology or cohomology is not equal to zero, means there must be somewhere some critical point, right? So there must exist a closed geodesic. But this sort of fact, you have to be a little bit careful what sort of conclusions you can get. So first, well, this homology is always non-zero, in particular because there exist constant loops. Like you will find the homology of your manifold that corresponds to the constant loop. So yes, you have found geodesics, but maybe you found some quite trivial cases. And the other thing that is a little bit irritating in this relationship is that once you have one geodesic, it is one critical point. Then you can, it's a closed geodesic, so you could iterate. You can look at twice that geodesic or 3 times and so on. So you have, in fact, infinitely many geodesics from the point of view of critical points, infinitely many critical points that could correspond to infinitely many homology classes. Nonetheless, there is a very nice theorem that I would like to mention here. So it's in 2 bits. It's really 2 theorems. One of them is to say, which is due to Denis and Michel Viguier-Poirier, saying that if you look at the rational cohomology as an algebra, if as an algebra it needs at least 2 generators, then when you look at the homology of the free loop space, this is really a mess. And it's a mess in the sense that if you look at the dimension as k varies, as the dimension of the homology grows, it will be an unbounded sequence. So it will grow in an unbounded fashion. Okay? And then
in fact, I remember in 67, Gromall asked me, what can you say about the Betty numbers of the free loop space? I said, oh, that's trivial, blah, blah, blah. And then he said, oh, you're talking about the base loop space.
Yes.
And I said, and then realize you have to, it's not known how to do this, right? So this came years later.
Right. Yeah.
The question was there because of this.
Right.
And it was already known.
So this result here is saying, well, if the homology is enough of a mess, is big enough, then it will get rid of this phenomenon. Then you don't have to worry about these iterates. You will. So this is saying you have infinitely many classes in homology, so infinitely many geodesics, but there are so many infinitely many that there will really be. Okay, I didn't write this down in the precise manner, but like primitive ones. They would. So the theorem says if
not power.
you will. Okay, none. There will be. If this sequence of numbers is unbounded, then whatever Riemannian structure you put on M, because this doesn't care about the Riemannian structure, right? So whatever Riemannian metric you put on M, it will have infinitely many distinct, what did you say?
Non-power.
Non-power. Non-power. Geodesics, okay? Right. So, so this is sort of a nice type of, geometrical information you could get out of the homology of the free loop space. Oh, yeah. This is for simply connected manifolds. Yes.
Yeah, but see, if the manifold has an infinite fundamental group, there are
then getting geodesics is a lot easier. So it's
the connected case was the unknown case.
it was the difficult case. And then, so what is the sort of leftover case? So the non-simply connected, whenever you pick a homotopy class, you will be able to find a geodesic in that homotopy class. And so if you have infinitely many different homotopy classes, you will have infinitely many distinct geodesics. What's missing is this way is the spheres and the projective spaces, because these are the spaces with they are simply connected, so the don't give you geodesics like this, but the cohomology has just one generator. So actually it's not known. I mean it's known for the two spheres that you always have infinitely many geodesics, but in general it's not known. Okay.
For any metric.
For any metric. Okay. So this is just using the cohomology of the free loop space, well, just a cohomology. So what we are going to do today is a string topology, which is adding a little bit of information, adding a little bit of structure to the homology or the cohomology. So we have our manifold, and we still have picked a metric, and we're going to add to this homology or cohomology. We're going to add some operations. Right?
Are you still assuming single connected?
No, I'm not assuming simply connected, and I'm going to be over the integers also. I'm not doing any rationality. Okay? Yes.
I had a quick question about, maybe I'm not understanding what the equivalence between geodesics is, but like there's this, if and only if you have infinitely many geodesics, if the cohomology is two generators, you said you exclude spheres from that statement, but like I can take great circles.
Did I put if and only if? I didn't.
For
any metric.
Oh,
okay.
But I shouldn't have put an if and only if, right? I wrote any metric. What?
It's not known.
There is, no, it's not known.
Whether there is a metric on a sphere or projected space that has infinity or not infinity.
Yes. Right. Okay, so here's sort of, we have this manifold with a Riemannian structure. So this is sort of my line of how fine invariants we could try. What sort of structure we might recover from our original data. So it could be the whole Riemannian structure. It could be maybe we only remember the differentiable structure, or maybe we only remember the homeomorphism type, or maybe just the homotopy type, right? The homotopy type, that's or less. I think the homotopy type from the homology of the free loop space, I think we can do. Right, so maybe, I think so. Right, yeah. So what we will do today is we will be a little bit like in between these two. There's something called simple homotopy type. I'll talk about this in a little bit, but for this we will. So this will be related to these operations, which is the string operations as defined by Mora and Dennis. And I'll start by saying a little bit about these string operations. Okay. So that's where we are going. Today. Yes.
For the theorem on the last slide.
Yes.
Is it sufficient that the minimal model have two generators, or is it at the homological level?
I mean, it's at the homological level, right? So, yeah.
It's not sufficient for the minimal model.
Sphere has two generators.
Yeah, the even ones do.
No, it's not.
Projective
No.
space has two generators.
Okay.
So the statement, just repeat the statement again. If it's not one generator, then you're okay. Then the statement is if you're not, the cohomology is not as one generator, then Como-Meyer applies.
Right. As soon as you have at least two generators in the cohomology.
Well, that's
not one generator. You prefer it as not
one generator.
more than one generator.
You
Yeah.
need at least.
Yeah, you need at
least.
least.
Need.
Yes.
Have.
You need at least. At least. Yeah. At least two generators. Yes.
And there's only one generator, no.
No. Yes. I mean, the theorem does not apply. Then we don't know. Yeah.
Yes, okay, I think you go to have, and you need to say need. That's right. Sure.
All right. Let's move on.
In fact, the statement is the Betty numbers are unbounded if and only if the cohomology ring is not generated by one element.
Yeah, so that you're saying this one is an if and only if statement.
Yeah.
Yeah. And I think the Gromel-Meyer is a one direction only.
What?
Gromel-Meyer is just one direction. If they are unbounded, then yes, infinitely many. Yeah, of course. I know that. So I don't know what I had on the slide, but so your theorem is an if and only if, like at least two generators, not one generator. If and only if unbounded sequence in the homology of the loop space, and then unbounded sequence implies infinitely many distinct geodesics.
Any metric.
For any metric, very important. All right. Okay, are we ready for string topology? Maybe.
Well, another point about this
No.
one, see, in the 60s, rational homotopy theory was regarded as trivial because spectrum, all tensor Q are all trivial, and then things like H spaces were rationally trivial, so it's all trivial.
Uh-huh.
And then when he asked this question, and I said, well, blah, 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 I answered real fast, No, that's the base loop space, which is an H space, right?
Yeah.
So that's why it's trivial for that case.
Yeah.
And then I realized, oh, they don't know this, and he'd been asking everyone, and this isn't known. So that means rational homotopy theory is not trivial. right? I mean, it was regarded in the last decade as trivial. Okay.
Yeah, it's a pretty cool statement, this one.
No,
Yeah.
There are other homology rings of certain, like 6 manifolds are much bigger than rational homology rings are bigger than, say, the classification of elliptic curves. You can check that too. So even the, so it was. So you have to not believe your elders completely, right? I mean, the prevailing wisdom was rational theory is trivial, or it's not interesting. So this, wow, this is surprising. It's not known, right?
Yeah.
Okay.
Very good. Okay, so what is a string topology about is, so I said that we were going to define some additional structure on the homology of the free loop space. We will use the manifold structure. Okay, so I'll allow myself that. And roughly what we want to use is we want to look for some intersections of loops, maybe self-intersections, and then we will use concatenations of loops or cuts when you have a self-intersection. Okay, so here, here's a first example, which is a product. And, you can think of 2 strings somehow interacting and then creating a new string, right? So that was the vague picture. So here's a more maybe serious way to think of it. Well, what's a p-homology class in the free loop space? For me, I think of a p-dimensional family of loops, hopefully even parameterized by a manifold. And then I have a q-dimensional family of loops, and I want to do an intersection. And what intersection I'm going to do? I'm going to do the one that is described by this picture. Here's my first, this represents my first family of loops. I'm going to look at the evaluation at 0. And here's the second family of loops, and I also evaluated 0, and I'm going to ask that these 2 points coincide. So I'm in the loop space, I have these families of loops, I evaluate down to the manifold at 0. This is now a homology class. I have my 2 homology class in the manifold. I can do an intersection product. Think, manifold represented homology classes. It's a transverse intersection. It will give me in the manifold a bunch of families of base points of my loops that will have dimension p plus q minus n. And then once the loops agree at the base point, then I can just concatenate the loops. Okay? So one can define this. So I told you what to do in case of transverse families represented by manifolds, by submanifolds, but you can do this. One can extend the definition to the whole loop space. And now you could also try to read this picture backwards and say you start from a single family of loops and you look for a self-intersection now, and if you have a self-intersection, you cut. Okay? Turns out that the interesting operation to do here is not just to look at a single, like a time 1/2 intersection, but it's good to look at all the possible times. So let your time vary along the loop and look for times where your loop crosses through its base point. Okay, so this will start with a family of loops. It will add a dimension 1 because I'm sort of adding this time parameter, and then it will do an intersection, so I'm losing n in dimension. Sort of to be completely.
So maybe it's just a typo in first one product there. LM cross LM.
Oh yeah, that is, yeah, sorry. Yeah, that's a typo. There's only a single, well, you do, yeah, I just want to concatenate, I do get 2 loops, I have 2 loops, but they agree, they have the same base point, and I want to concatenate, and I get into LM, yeah, thanks. Oh yeah, and n is the dimension of the manifold, yeah. Each time I do an intersection, I will lose exactly the dimension of the manifold. More typos, more undefined. Sorry. Okay, so if I have to be completely honest, and we will come back to this, this operation is really most naturally defined as a relative operation. Because what I do when I have a family of loops, I'm gonna cross the family with the interval, and the interval has a boundary, right? 0 and 1, and that boundary will be carried around in the operation, and it will create constant loops on the one side or the other side, and then you might as well sort of mud out by the constant loops. This one is not so important. This one is sort of really, you can hide it in all sorts of ways. There are ways to define a non-relative operation, but this is the true coproduct. Anyway, we'll get back to this boundary issue in a bit. Okay. So just to give you a little flavor of what you can do with string topology, something I proved with Nancy Hingston some years ago is, if you look at this coproduct I just defined, so the one that split the loops, looks for self-intersections and cuts, it will detect unavoidable self-intersections in homology classes, in the sense that if it is non-zero, then there must be some, think again of homology class as being a family of loops, there must be some loops in your family having a non-trivial self-intersection. So, for example, think of, in a surface like this, if you have this, if you look at the one parameter family of loops, which varies the base point along the, rotate the base points along this loop, and otherwise follows the loop, then whatever you do, you will never be able to deform away from having at some point one of the loops crossing itself at time 0. That is, having its 0 over here. You will actually have two loops like this. But this works also for higher. So higher, you can apply your coproduct several times. So look for self-intersection several times in a row, and that will look for what seems quite unlikely, which is like a loop that is crossing itself many times. So in a high-dimensional manifold, you would say, well, this never happens, right? But if you're looking at a large family of loops, when the coproduct, this iterated coproduct, is non-zero, it tells you that whatever you do, you will always have in your family something that looks like this. And this coproduct is a non-trivial operation, for example, on the homology of the free loop space of spheres. And on spheres, this statement is actually an if and only if. So you will be stuck with such self-intersections if and only if this coproduct, higher coproduct, is non-trivial.
What does the tag means is happening on this side?
So the statement is, if you have your homology class, if when I do the case iterated coproduct, I get something non-zero, then any chain representative of my homology class will have to have a loop that looks like this, with, k will pass k plus 1 times at some point. There will be a point where the loop passes k plus 1 times. Yep.
Would that work for the co-bracket also? Because there's no base point.
Right. Yeah. So that's. Here I'm thinking I have a base point and I'm varying the base point along the loop. So I'm looking at all the positions, all the possible positions. I assume there is such a similar statement, for the bracket. So which would be the S1 equivariant version of this. Okay. So there's a whole world of possible string operations. We know them quite well algebraically so this relates to Manuel's talk. Where's Manuel? There. Yesterday. So yesterday Manuel touched a little bit told us a little bit of the string topology on, in Rothschild complexes and things. So there's a wild world of operations one can define, like, what's the rough ideas? You have a bunch of loops, and you do these things we talked about. So you have a bunch of loops, and you declare, okay, I want some self-intersection. I choose my pattern of self-intersection. I say this point I pick some points along the loops and I say these two should be equal, these two, and maybe these three or something. And once, so I look for these self-intersections as a subspace of the loop space. I intersect with that subspace, and once I am in that subspace, then I can read new loops by concatenation and by cut maps. So I could go around like this and come back and maybe read another one here and maybe read twice around this and then cut around here. I'm free to do all sorts of stuff. Okay, so there's a wide world of string operations, and so far, well, the ones we understand best are the two I described a little more precisely at the beginning, which is this product and this coproduct. The rest is still a jungle. Okay, so I said that, so this was my short intro to string topology, the sort of geometric side of string topology, and now I would like to do a little digression about the classification of length spaces, because I have to talk also about simple homotopy. So, and I'll be talking about three-dimensional length spaces. So what are these? I take the three sphere. You can think of it as sitting in the complex plane C2, and then the length space LPQ. So I pick a P and a Q, which are co-prime, and it is obtained by quotienting out the three sphere by the relation, rotating the first coordinate by e to 2 pi I over p, and the next coordinate by e to 2 pi I q over p. So you do it sort of a twisted rotation. Okay, and length spaces were classified a long time ago by Reidemeister, and the classification says something like this. So here P is a fixed prime, and the classification says LPQ is homotopy equivalent to LPQ prime. There's a prime missing over there, right? Oh, the prime is also missing down there. Okay, so LPQ is homotopy equivalent to LPQ prime if and only if QQ prime is a square modulo P, plus minus a square modulo P, and it is homeomorphic, or actually in this case it's equivalent to say whether it's homeomorphic or simple homotopic. I'll say what this is in a second. If and only if, well, some stricter relation. So the square is plus is 1, or the one is plus minus the other. And what is this simple? So a simple homotopy is defined as a homotopy equivalence that can be written as a zigzag of what is called an elementary collapse. And what's an elementary collapse? Well, it's a small collapse of a set. Like you think of, if you had a triangulated manifold, then you would be collapsing a triangle, or one of the, and then you do a zigzag of, so it's a sort of, it's a nice type of homotopy equivalence. And the proof of this theorem uses something which is now called Reidemeister torsion, and that's a very subtle invariant that is obtained from, you have your manifold, you pick a cell structure, and then you go to the universal cover, and you pick some, now you look at this Z pi 1, you get a Z pi 1 complex out of your cell structure. You pick a representation to make this an acyclic complex. And once you have an acyclic complex, you know that, and you pick also a basis for all of this, then you know that if you take all the odd guys and all the even guys together, then the boundary map must be an isomorphism. It will be a matrix which is an invertible matrix because the homology is 0. So you know it has to be an invertible matrix. And then you take a determinant. So it's a sort of, it's a construction which is a little crazy because you make a million choices that seems quite unreasonable, and you get a number out, and somehow this tells you something about your manifold, which is independent of all your choices. And in particular allowed to classify these length spaces. Yeah, and so there is something called Whitehead torsion, which is basically the same, but done for a map. When you have a map, you can associate a cell complex by looking at the mapping cylinder, and then you can do a similar construction. Okay.
So why is that not a homotopy?
Now, why is?
Is there an idea for why it's not a homotopy invariant? We're so used to homology being a homotopy invariant. It's kind of a homological construction.
Yeah, why would it be? Why is it an invariant at all, right? I mean, it's like, so you're making a construction that depends on a homotopy equivalent, can completely mess out your manifold, right? So you start with a cell structure, just the fact that you start with, a cellular complex, right, is really not something that is preserved at all by a homotopy equivalent. Exactly. Like, a homeomorphism does not respect the cell structure either, right? It will give you a new cell structure. I guess that's, and I guess a simple homotopy it's something you can control on the level of cells. Maybe it's reasonable that it's a simple, yeah. Anyway, so Whitehead torsion is exactly what detects whether homotopy equivalence is simple. But it's not an easy thing, right? That this sort of zigzag of elementary collapses should have, it's a single elementary collapse is an easy thing. The problem is an inverse of a simple, a composition of an elementary collapse one way and an elementary collapse the other way. This is not something you can describe. At least not I mean, I don't know. It's something I found very difficult to grasp. Yes.
Reidemeister torsion is for a space, and Whitehead torsion is for a map.
Yes. And so Reidemeister torsion, you will also pick a representation because you need an acyclic complex. Whereas for the map, you will create an acyclic complex more naturally. Yes. Right. So let's go back to our string topology, and we were talking about trying to detect. So I said we were trying to detect something more subtle than the homotopy type using the homology of the free loop space. But if two length spaces are homotopy equivalent, then the loop spaces are homotopy equivalents, and therefore the homology are isomorphic, right? So if you just use the homology, you're not going to get any further. So there's a theorem of Ralph Cohen and Dennis and John Klein from some years back that says, well, actually, if you have two homotopy equivalent manifolds, then you will get, and you look at the homology of the free loop space together with this string product we had at the beginning of the talk, then they will be isomorphic as algebras. Okay? So you have not gained any extra, past the extra information past the homotopy type with the product. But then, so a couple of years ago, Florian Neff, who was also here, showed that actually for these three-dimensional length spaces, well, you don't, and if you look at the coproduct instead of the product, this string coproduct we talked about, you can have something which is not, even though they are homotopy equivalent, these need not be isomorphic as co-algebras. So using the coproduct, and so this is a result we extended together also with Manuel Rivera by saying that actually the length spaces are homeomorphic or simple homotopic if and only if these co-algebras are isomorphic. So the homology together with the coproduct, and it's enough to consider the three-dimensional homology. If you look at the coproduct on H3. If they are isomorphic, then the two length spaces must be simple homotopic, which means they will also be homeomorphic. Okay, so the co-product is somehow detecting more. Yes?
How computable is the thing on the right?
Right, so that's you know, what is really beautiful with this is you can just do the computation like geometrically. So we're talking about H3 of the free loop space on the length space. So the length space is three-dimensional. So we're talking about classes that are of the same dimension as the length space. And the classes we use are just, you know, they all evaluate to the fundamental class. And then, you know, that means that for every point in the loop space, in the length space, I need to give you a loop. And what you do is you can use, I mean, we will have classes parameterized, so by the length space itself, so that's a manifold, that's nice. And we'll describe loops by using the residual circle action that, you know, remember the length space was defined as a quotient of a ZP action on S3, but you still have, you know, a torus action you can use. And so we will pick loops in that torus to describe classes. Now, they are manifolds, and it will be a question of, you know, we have, I mean, you need to do some sort of transverse intersection to do these computations, and then, you know, you will have to wiggle them around, but like it's really, it's a completely geometric computation. Yeah. It's the same with spheres. I mean, the loop space on spheres, you can just compute the product and the co-product by, they are nice representatives of the classes, and you can just do intersections. So that's a, yes?
What's the time frame for when this was discovered?
This is 2000, like, you know, the preprint is probably 21, but it was, I know it was the beginning of the pandemic, because I know I remember very well, I received an email of, so the story is, you know, I had a proof that this could not happen. Right? So Florian emailed me, I would say probably in April 2020, because I know where I was with this example. And I spent several months, you know, between trying to disprove his example and trying to disprove my theorem until I found out that his example was correct and I found a mistake. Yes?
Oh, it's just that Florian was invited to give an Einstein chair seminar March 19th, 2020. And March the 12th, everything started shutting down, and I canceled, sent him an email, so sorry, we're canceling the lecture.
Yes, I see. You would have heard it exactly at that time.
Exactly March 12th, when the lecture was canceled.
Yes.
It's going to be about this.
Yes. Very good. Well, was the sort of for the product, this is like 2012 or something like that. Huh?
He hasn't come yet. Did he come to the
Oh, he's here.
He's right there.
Where? Oh, hi. That's true, right? Okay. Very sad. Okay.
All right. Okay, so let me just give you a slight idea of you know. So that's the example Florian computed first. You take L71 and L72. These are two length spaces that are known to be homotopy equivalent. This is one of the first homotopy equivalent but non-homeomorphic length spaces, and you know they are so. He computed that they was, you know, they are as co-algebras, the homology of the free loop space could not be the same, could not be isomorphic. And, you know, you can interpret this as saying, well, you know, whatever, if you have a homotopy equivalence, if you try to write a homotopy equivalence between these two spaces, it will necessarily mess up the loops. Right? That's the idea I want to get through. And so what does you know, if I had to write down a homotopy equivalence, so there's a recipe to do this. And the recipe goes like this. So you start with your first length space. That's my L71. Then you pinch out a three sphere. So you take a little disk and you pinch out, you make it a three sphere. So I made it big too, so we see it. And then, you know, now you can use on the length space, I'm going to map to the other length space, but I can't just do, you know, remember these length spaces are defined using an equivalence relation, and to make these equivalence relations work out, really, you can't easily write a degree 1 map. So, but you can write a degree 8 map between these two. It's not difficult. You just do times 2 on the one coordinate, times 2 on the, times 4 on the other, and that works out. So you have a map here. That's this map, and then on the sphere you just do a degree minus 1 map. Okay, and then finally, so L7-2 goes to itself, and then S3, well, you have this degree 7 map, which is the quotient by Z mod 7. Okay, so in total, I have done degree 8 minus 7, which is 1. Okay, but even though it's a degree 1 map, if you think of a point here, it really thinks, it looks more like a degree. It's like it's a really messy map, right? I mean, it took a little neighborhood here and wrapped it around the length space 7 times, and the rest, it wraps it 8 times. So it looks more like, if you ask a point here, it looks more like a degree 15 map. Yeah.
So there's an older result about L7-1 and L7-2 saying something like they're homotopy equivalent, but their configuration spaces
of 2 points. Yeah.
Is there something similar about the idea here, or
no? We don't know how to relate these two facts. So this is this is paper of Longoni and Salvatore saying that for these two same length spaces, the configuration space of 2 points are not the homology of the configuration space of 2 points. They have these massive products that are different, and we don't know how to relate the two results. But yeah, they should be. Also because the configuration space of 2 points is hanging out here. What did I do for defining this coproduct? I looked at 2 points, right? And we're really thinking of these 2 points. I mean, I'm making them equal. I'm looking at an intersection. So in sometimes I'm looking at the diagonal, but in the definition, really the complement of the diagonal is very important. That's exactly the configuration space.
So configuration spaces are not homotopy invariant constructions.
Right. Yes. Yeah. Yeah, and that was, I think that was the first example. Yes.
Yeah, that theorem, when it came out, Lippmann Bears has this definition of the theorem, which is when you see it, you want to steal it. And that's what I felt. That's all that is.
Yes, yeah, it's a very
all
nice
the
thing.
pieces were familiar, but
yeah.
The Longoni.
Yes, yeah.
Salvatore.
Yeah. Very nice thing.
Really quite.
Yes. Okay. Yes. So what I want to do now, for the rest is somehow, I want to get this idea that, we'll use loops to detect how messy a homotopy equivalence is. Well, you should think of a homotopy equivalence which is not a simple homotopy equivalence. A simple homotopy equivalence is just doing these elementary collapses and inverses of such. And we want to detect homotopy equivalences that are not simple. And we want to say a non-simple one is going to be messy, whatever that means. And I'll give you a version of what I mean by a messy homotopy equivalence. Okay, so a question you can ask now that we have these examples with the length spaces is, if I have a homotopy equivalence between two manifolds, and I pick a homology class in the loop space of the first one, we know that the map is does not induce necessarily an isomorphism on the homology of the free loop space as of co-algebras. That is, we know that if I first apply the map and then the coproduct in the second manifold, or I first do the coproduct in the first manifold and then apply the map, I might not get an equality, right? So the difference between these two things might be non-zero. So I can ask, well, what is this difference? Can I express it in a way that is in terms of the map in particular? Okay, and in terms of the map, and in terms, of course, of the homology class. So I'll give you two formulas. So the first one is due to Florin and Pavel Safronov, and it says the following. So this is this, right? So this is the difference between applying first the coproduct, then the map, or first the map and then the coproduct. And it says, well, it's something product, string product with the image. So in the second manifold with the image of my homology class minus the image of my homology class string product something. So what is that? What is that something? That something is when you take, I said to a map you can associate something which is the Whitehead torsion, which is something that detects whether a map is a simple homotopy equivalence or not. And then, well, the Whitehead torsion lives in something which is called the Whitehead group, which is basically K1. It's a quotient of the K1 of Z of pi 1 of your manifold. So there is a map which is called the Dennis trace, which goes to, well, Hochschild homology, or if you like, the homology of the free loop space. Right? And so this, and it will land, the Whitehead group will be mapped to H1 of the free loop space. So given a map, you have this invariant which is called a Whitehead torsion, then you can take a trace of it. So we're having a residual invariant which lives in H1 of the free loop space. And then once we have this element in H1 of the free loop space, we can take the diagonal. So in H1 of the product, free loop space times free loop space. So now we have two loops, and one of the loops we will product it, string product with our homology class, or product on the other side. Okay, and keep the same. Okay. So right, and here's a second formula, and the second formula, which came out of this wrong proof I had of together with Nancy Hingston of saying that this was zero. So so we get the very same formula, but this tau f, this Whitehead torsion, is replaced by something else that I'll describe now, right? So remember this thing here, it was obtained by, you take the mapping cylinder of your map, you create a cell, you choose a cell structure for this mapping cylinder, you go to the universal cover and all sorts of things, you have an acyclic complex, and from there you get out of matrix, an invertible matrix, and you take a determinant. And now instead I'm going to do something which is in terms of F, which is a geometric definition in terms of F, a homotopy inverse of F, and some more homotopy. So a quite different definition. So here it is. So we start with a homotopy equivalence. If I have a homotopy equivalence, I can pick an inverse, and this will come with, if it's a homotopy inverse, then I'll have homotopies witnessing that this is the identity, and a homotopy there witnessing that this is the identity. Okay, and it turns out that actually you can pick a little more. You can if you choose. So you should think of this data as, I start with F, then picking a homotopy inverse, and this H1, this homotopy is a contractible choice. It's like a little bit, it lives in a path space-like thing. And then if I pick H2, I can pick H2 and a second homotopy, which I call K, which is a homotopy between the following two maps. If I go from M1 cross I to M2, I have two ways to go with these maps. I could first apply H1 and then F, or I could first apply F and then H2. These are two different maps, and you can choose H2 given F, G, and H1. You can choose H2 such that K exists, such that such a K exists, and this is a contractible choice. So all of these data given F, all of these data is a contractible choice. Okay. So this is one part of the data, and the other thing that will show up here is what I like to call the fake diagonal. And so the fake diagonal is, if you look in your original manifolds, is the points in M1 cross M1 such that F thinks that they are on the diagonal. So they are mapped to the same point by F. So remember, this homotopy equivalence we talked about on the length space, it was highly non-injective, right? Most points in the target would have, they would have 15 points that were mapped to them. So this will be a quite different.
So this is cycle. It looks like a cycle, that right dimension.
Right. So I want you to think of this. So this includes the diagonal, right? And in my dreams, this is the diagonal union another manifold of dimension n, right? And I have no idea how to prove that, and I have no idea how to prove that this is a homology class of dimension n. But I can deform it a little bit. If I deform a little bit, instead of using f, I'm using f twice. That's the problem. If I use f cross f prime, a small deformation, then this is a correct. Then this is an n-dimensional submanifold. I can make it an n-dimensional submanifold. So I'm lying a little bit here. This is the object that this is the object at which.
It's a cycle.
Huh?
It's a cycle, though.
In what sense is it a cycle? How is it a chain? I don't know how this is a chain. I simply don't know where to start. Yeah. I can show. Let me just draw. If you do a homotopy equivalence from the interval to the interval that goes back and forth like this, right? This diagonal, this fake diagonal, looks like this. Yeah, totally. I mean, but it's the only example I can draw, right? So that's not a proof. Yes. Anyway, I definitely, it shows up as a cycle, right? But of course it doesn't show up exactly as this one. But this is morally what it wants to be. Anyway, so we will pretend it is exactly that. Okay. So here's, I have to give you. So what do I have to give you? I have to give you a one homology class, a homology class in H1 of the free loop space of my second manifold. Right? That's what I'm supposed, from this data, that's what I'm supposed to do. And exactly, I want you to think of this as an n+1 dimensional family. So I'm taking this fake diagonal, which I think of as an n-1, as an n-dimensional manifold, or a union of an n-dimensional, something. Anyway, I'm thinking of it as an n-dimensional thing. I cross it with an interval, so it's n+1 dimensional, and I'm going to do an intersection in a little bit. So I'll go down to dimension 1. Okay? So we start in dimension n+1, and this is my m1 and this is my m2, and I have an element, mm prime in the fake diagonal and an element t in my interval. So these are two distinct. It's only interesting for the points that don't come from the diagonal. So I'm taking 2 points that are distinct in M1, but they are mapped to the same point in M2, okay? They're distinct, but they map to the same point. So when I go back, if I look at G of f of m, these are the same, right? They're the same, and I also have this H1 that gives me a path from the one, from these points to this common G of f of m. Okay, so this is H1 for m, and this is H1 for m prime, right? And then I can map this information back over here. F of H1 is, is now going its way here. The one coming from m, and f of H1 for m prime is somewhere else, right? These are different paths in the manifold. But they are not unrelated, because I also have yet another, this is f of g of f of m, and I have another way to go here, which is h2 of f of m, which is the same as h2 of f of m prime. So I have a common path here for the 2 points, right? And that map K is exactly relating these two things. So K for m is relating these two guys, and K for m prime is relating these two guys. Okay?
The significance of the purple.
Okay, so the purple is where we are going. So I had to give you a loop, right? So given all of this data, I want to give you So I want to give you a loop, and the loops by doing an intersection, because I was going to go down by n in dimension, and my intersection is happening here. I'm looking for the point such that given t, these are equal. These two paths might happen to intersect. Could happen. Okay. If they intersect, then these 2 points, their images are also the same. So when I go across, this becomes a loop. That's my loop. Okay? So the claim is that this torsion, this thing measuring how bad my homotopy equivalence is measured here by the fact that sometimes in such homotopy, you will have a path here between these points which is long, which is not a little. If it was a small path, then it wouldn't count in this business. But so that means that for a homotopy equivalent which is not simple, I will not be able to choose H1, H2, and K such that, these things always are small. So I'll be forced to go through very long paths, and very long paths that sometimes have a self-intersection coming from here. Okay?
And for a simple homotopy, this loop will be in a contractible set.
Right. So I don't know that directly.
Oh.
So yes. Oh. So this is a question. Oh. Like, yes, of course. It's a very frustrating thing, because if you for an elementary collapse, yes, no problem. Like an elementary collapse is a very simple thing, but for a map which is a composition of an elementary collapse and an inverse of an elementary collapse, I don't know how to do it. I don't have a direct proof yet. Yes.
Can we see at least from this picture that C vanishes was a little group?
And I don't see that either. This whitehead torsion is 0 if there's no fundamental group, because it lives in a group that is 0. So there are, all homotopy equivalences are simple. But I can't directly in this picture. I still don't know how to show directly that if there's no fundamental group, this vanishes. Yeah.
Yeah, I'm curious about what category of manifolds this all applies to. Should it just be topological manifold? It seems to be using DL structure or something.
I don't dare to answer such questions. I don't know. Yes. Yeah, this could be certain questions. So I don't know. Yeah.
Well, usually geometric operations require a geometric structure on the manifold.
Yeah.
If there are theorems that say that whitehead torsion is topological invariant, you can't
define
it this way.
Mm-hmm.
There's no transversality.
Right.
That's naive. Correct.
Yes.
What on the slide is more than topology? More than topological structure?
Oh no, yeah, you're right. I mean, this is defined where I did an intersection here. Yeah. Yeah. So all my intersections are big capping with a Tom class. Yeah, I do that all the time. And actually, this one also shows up as coming from capping with a Tom class. Which is
because the Poincare rule of the diagonal. Intersection theories is not.
Yeah, intersection, yes. So intersection theory. So this is sort of, yeah. On homology, yeah. So it's exactly, yeah. Somehow the sort of, yeah. If what we're doing an intersection product in the manifold, but we're lifting it to the loop space, and somehow there's a mess that comes up from lifting it. This mess comes up from lifting that to the loop space.
But in particular, the Chas Sullivan product, for that you only need a Poincare duality space. You only need Poincare duality to the ninth. But in this co-product that you're working with, you need something more. That's the upshot of these theorems.
Is that explicit? Like, for example, if it said, well, Is there locality of the top class somehow used here? Is there locality of the top class somehow used here?
What do you mean by the locality
So
of the
that
top
would be
class?
something that is not a homotopy invariant.
What do you mean by the locality?
It's concentrated near the that. As a representative.
Yes, you use that, yeah.
You use that?
Yeah.
That's not a homotopy.
Yeah. Do you want this last slide? Yes. Okay. But we're a little, you guys are like, it's okay. We keep going. We're little, these are my numbers, are sort of my estimates, time estimates. We'll do a last slide. Okay, so I just want, the last thing I want to give you is an idea of where this formula comes from. Over the 20 so years I have known Dennis, I feel like every time I meet him, he says chains, right? And every time in my head I go like, yeah, sure, Dennis, you say chains, but so far homology is good enough for me. But I think it's the first time I really need the chains. So it's like cool. I was like, yes, and he was right. Actually, chains was useful. Finally, 20 years, So anyway, so here are the chains. Okay, so here's a little fact. So how can you get to the formula? So this co-product we talked about, as I said, we crossed with the interval. So we have to do this operation relative to time 0 and 1, because that's a boundary. Otherwise I can't define it in homology, right? So we'll be relative to these things. And there's this idea that is already in the work of Hingston that you can reparameterize the operation. You can always set t equal to 1/2. But when you set t equal to 1/2, this t0 and t1, t0 is going to create half constant loops. I mean, this half of the loop doesn't exist because you force t to be 1/2. So it's really a constant loop on the one side or a constant loop on the other side. Okay? So looking at this operation is really the same as looking at this one. This is like the important part of the operation, is doing this intersection at time 1/2 only, but relative to half constant loops. Yeah, so that's one thing we can do. And then the second fact is that actually that operation has been known for a long time to be trivial. This was noted by Tamanoi, and what is the idea? Well, the idea is if t is equal to 1/2, well, it could just as well up to homotopy be equal to 0. You can push it to be 0, or you could push it to be 1. And when you combine these two facts, it's not only that it's just doing a little thing around 0, 1, but it can only do something non-trivial on the fundamental class of the manifold, and that's it. So it's really almost a 0 operation. If the order characteristic is 0, then it is the 0 operation. Otherwise, it does this one thing in the fundamental class. So in particular, it is an operation that is invariant under homotopy equivalences. But what is happening is that when you try to write on the chain level that this thing is trivial, then the chain homotopy is not a relative chain homotopy. So this, we cannot keep that relative part fixed, right? So if you put these two things together, what it is saying is, if you pick a chain homotopy for this trivial coproduct, witnessing that this one is invariant under homotopy equivalences, that chain homotopy, well, it will give you a formula that looks like this, just because that's the way relative homotopies work. It will say the failure of invariance is given by d of h plus h of d, and so now this we go back to homology. We used the chains for a second to write this formula. Now we go back to homology. This term goes away. It's a boundary, but this one does not need to be a boundary, and this is where our homotopy comes in, and why and our two terms they're exactly here. What do we do? We really apply this to our original homology class in the free loop space cross an interval, and that has boundary exactly the homology class cross 0 minus the homology class cross 1. And these were creating these half-constant loops, right? So I'm looking at my original homology class, and I'm sticking half-constant loops at the beginning of it or at the end of it. And then, you know, what you see is somehow the chain homotopy that, you know, applied to any homology class will not really care about these loops that you attach to the one side or to the other ones. It will only care about, you know, what has happened to these constant loops. If I know what happens to the diagonal, thought of it as the constant loops in my original manifold, I will know what happens to any homology class, and it will give you a formula like the one I gave. That's what I wanted to say.
Thank you. This is like string topology, taking little pieces, selecting them in the original time, doing these things, with all these big features.
Yes. Yeah.
Thanks for the great talk. I was just wondering about your decision to express this in terms of like simple homotopy versus saying it's just not a homeomorphism in there. Okay. I mean, that it's you know, for the lens spaces, right? They're not they're homotopy equivalent, but they're not homeomorphic. So I don't understand the simple homotopy.
I don't either. So, I mean, like this is like it's a subtle invariant, right? You know, why is a I mean, how on earth do you understand what's the difference between a simple homotopy and, like, between a homotopy and a homeomorphism? It's clear, right? But right. A simple homotopy is like, it's an in-between concept that has, you know, a slightly strange definition. And you want to, so what I'm trying to say is somehow, you know, there is this strange definition, there's this definition that says, well, a simple homotopy is only doing small things, right? And so if it isn't a simple homotopy, then it should not be doing small things, it should be doing big things. And that's what I'm, you know, what I have as an invariant seems to be detecting doing big things. But I don't even have a proof that this is exactly the same as detecting simple homotopies.
So pulling on that again, it's not that I have thought too much about this notion, but since you already have a metric, the notion of control topology.
Yeah, I know. Yes. So yeah, I was recently talking to Wolfgang Lück, who was saying, yes, this sounds right. I mean, it's not like he could say yes because blah, but he said this sounds right from the point of view of control topology. Simple homotopy should be small.
I mean, it's related to what John asked, probably not very direct, but related to your talk. So if you have X and Y are homeomorphic, their configuration spaces are homeomorphic. If they are homotopic, then configuration spaces may not be homotopic. We can ask if X and Y are simple homotopic.
Yes.
Can you say anything about their configuration space?
I don't think we know that now. Yeah. I mean, this is like this is a very natural question. Yeah.
You can take, you know, Euclidean space and configuration space at 2 points. That different homotopies. There's simple homotopies.
You say
just the Rn?
Yeah.
Oh, different RNs. Yeah. Closed. Overwhelmed, yes.
Can you ask the question again? What's the question?
Let's say X and Y are two manifolds, compact manifolds, that are simple homotopic. Can we say the configuration spaces are homotopic or something?
Yes, well, what about simply connected manifolds? Then homotopy equivalent would imply simple homotopy equivalence. So let's say you're,
But length space is like, yeah, okay, yeah. Yes.
right. So that would say, for simply connected manifolds, two-point configuration space. So, yeah. So if you take a complex projective space, something that looks like complex, when you look at M cross M, and you remove the diagonal, then if the two-point configuration spaces were the same, then that complement would be the same, right? It'd be homotopy equivalent. But what is that? That's you remove a point from projective space, and that gives you the projective space homotopically at one less dimension. So you get a projective bundle over the projective space, right? And now the homotopy type of a projective bundle determines determines the Chern classes rationally, because it's a splitting principle, right? So this bundle, you would know its Chern classes from the homotopy type, but there are many manifolds that have the homotopy type of projective space that have different characteristic classes. So it wouldn't be true. I don't think.
Thank you.
I've been trying to use that to prove something. I didn't just think of it now.
Thank you.
Anyone else? Okay, let's thank Nathalie.